Okay, guys, let's talk about 15C, which is conjugate. Sorry. The conjugate, so let's see, 15C is conjugates. And the idea is if we let Z is equal to X plus IY, then the conjugate, I don't know why I don't say at the beginning of the board, the conjugate, which is denoted as Z star, or something you might see it as Z bar, is X minus IY. Now, what's going on here? So, algebraically, there's a couple of interesting properties. So we have, for example, if Z equals, 8 plus 2, if Z equals 8 plus 2I, then the conjugate is 8 minus 2I. And if Z is, 3I, then its conjugate is negative 3I. Keep in mind the geometry, because once again, we're training ourselves to think of numbers geometrically. We'll get to that in a second, but kind of say, oh, you know what? It's 8 plus 2I is up here, 8 minus 2I is up down there. If 3I is up here, then negative 3I is down here. Yeah, interesting. Some algebra, we know that a number plus its conjugate, which is x plus iy plus x minus iy, is equal to 2x, which is 2 times the real of z. Interesting, right? What about the difference? What happens when we subtract a number and its conjugate, x plus iy minus x minus iy? Well, we have 2iy. Well, that's 2I times the imaginary part of z. And we saw it when I spoke about this in a previous lesson, though if you're seeing this for the first time, we're going to see how this is going to be important. We're going to need these two things. How about product? What is the product? Well, from last year, we can see x plus I times x minus iy. Well, this is the difference between the difference of two conjugates. It's no different than the reals. So we know it's x squared minus iy squared, and we get, finally, x squared plus y squared. Now that's interesting because we weren't, and which we also noticed, this is actually, it's the modulus squared. A complex number times its conjugate is equal to the modulus squared. Now, this is important. And if you remember, when I did complex numbers, I did addition, subtraction, but I did not, and multiplication, I did not do division. So now we're able to do division. And the issue is, in the same way we don't like zeros in the denominators, we don't like radicals in the denominators, we also don't like complex numbers in the denominators. And so by multiplying a complex number by its conjugate, we actually rationalize it, right? Think about that. We rationalize the denominator, right? That's kind of interesting. Just a little thing I bring up is, if you think about this, let's say like 2 plus 3i times 2 minus 3i. So I want you to visually be like, okay, I'm multiplying two complex numbers together. 2 squared plus 3 squared is 13, right? And this is kind of interesting because you say, well, 13 is a prime number, but that only goes to the natural numbers. 13 is not the product of two complex numbers. Once again, that whole theory about prime numbers, that only applies to natural numbers. Outside of that, that doesn't hold. So let's do division. So I have 1 divided by 2 plus 3i. I have a complex number in the denominator. I don't want a complex number in the denominator. So I'm going to multiply it by its conjugate, because well, we didn't tell, yeah, a complex z divided by z. Yeah, z divided by z is 1, as long as it's not 0. So we have 2 minus 3i divided by 13. You can leave it like that. You saw in the textbook, sometimes they split up the fraction. That's totally up to you. If you want to decide that you want to like simplify or reduce, that's your call. How about a 3 minus 4i divided by 2 plus I? Same idea. Once again, it's not a difficult concept. It just gets a little tedious. You'd multiply top and bottom by, what do you think? Exactly, 2 minus I. And so I like to do the denominator first. It's clear that I have 2 squared plus 1 squared, or 5. And the numerator, yeah, it's a lot of work. It's tedious, but it's not a big deal. I mean, you could do like a box on the side, because you need, can you see? Yeah. So I have 3 minus 4i, 2 minus I, 6, negative 8i, negative 3i, and let's see, 4 times 1 is 4, negative times negative is positive, but I times I is negative 1, negative 4, final answer, 2 minus 11i. And you can split it up if you want. Now, let's get to the geometry. So we know that our cis, right, represents a complex number, right, whose modulus is r, and whose rotation is theta. So this is r cis theta. Once again, it was like x plus iy. But that was the last. So we understand the conjugate. So what's going on with the conjugate? Well, the conjugate, this is x minus iy, right? This is x minus iy. So what do you think that is, how do we think we represent that as with an argument, with a modulus and its argument? Well, visually, where is what's going on here? We know that this is x and this is y, and we know that this is also, this is negative y, but it's still the same length. We know this is r, so from geometry, we know these two triangles are congruent. That means this angle is also theta, but it's a different direction, it's negative theta. So we see here that if the complex numbers are cis theta, its conjugate is r cis negative theta. And that totally makes, we're negating, yes. So the rotation, yeah, the idea, yes. That's it. And use a negative rotation will make your life so much easier. So you know what? If a complex number is, let's call z is, I don't know, how about 10 cis 45, the conjugate is 10 6 negative 45. And then I realized I don't think I talked about exactly what cis is. I don't think I talked about what is r cis? Well, r cis is r times cosine of theta plus I sine theta. And that's equal to r cosine theta plus I times r sine theta. And if you recall from our diagram over here, right, we have the triangle. This is x, y. We said this is theta and this is r. And this was just x and y. So we know that r cosine, this is x. And we know that this is y. That's all it is. I'm not sure if I spoke about it or not. I'm realizing I kind of forgot, but that's where it comes from. Yeah, this is x, and this is what, right? Because cosine of x, theta equals x over r, so x equals r cosine theta. and sine of theta equals y over r. And so y equals r sine theta, and we just suck it back in here. Yeah, that's it. I wasn't sure if I spoke about it or not. That's the idea. So keep that in mind also. Let's continue. And then there's just some basic exercises. Let me get the eraser. Some properties of conjugates we're going to need. Let's see, property of conjugates. The first one, the one in the book, but it's a really cool one. The idea that, let's say that Z and W are complex numbers, right? Z and W are elements of the complex numbers, and I want to show that that the conjugate of the product of two complex numbers is equal to the product of the conjugates. And so the proof, you might actually be asked to prove this on the exam. So let's let Z equal A plus BI, and let's let W equal C plus DI. And so Z times W is, it's like the FOIL method. I'm going to multiply this. So it's AAC minus BD plus AD plus BCI, right? And so the conjugate of this is AC minus BD minus AD plus BCI. And so dot 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 dot. Now let's see what Z conjugate times W conjugate. That's A minus BI times C minus DI. Well, we have AC. I want the real parts. So I know the real parts are A times C and the BI and the DI, because the I's will cancel out. The negative times the negative becomes positive. B times D is BD, but I times I is negative I. And so we have AC minus BD. And then the question is, what are my imaginary parts? Well, the imaginary parts are A times DI and C times BI. And we see that they're equal, and therefore we prove this. What are some other cool rules? The other rules are other rules. We have the sum and the difference of a conjugate is equal to the sum and difference of the conjugates. We also have the division rule. The conjugate of the division of two complex numbers is equal to the quotient of the conjugates. It seems very good, but once again, this is something new. We have to go through the grades. So now we're about like 6th grade, 7th grade. We're getting to the good stuff, but we have to build up the unit. My favorite one that I love, are you ready for this? If you take the conjugate of a complex number raised to a power is equal to the conjugate raised to the nth power. And so the homework assignments, it's basically just manipulating the rule. I think there's a mistake in the example in the book when they ask you to take the conjugate in terms of W. I think they mean find Z conjugate in terms of W conjugate. So here are the rules. Work on the problems. This is 15C.